Hi everyone, welcome back. Today we are going to start a new topic, which is spherical wave functions. In the last couple of lectures, we looked at cylindrical wave functions, cylindrical waveguides, and fiber optic cables. Today we'll move on to spherical wave functions, and we look at problems that have some kind of spherical symmetry. Okay, so why do we care about spherical wave functions? They're actually very popular, not just in electromagnetism. You'll also find them in quantum mechanics. You'll find them in all kinds of problems in field theory and so on, where you have some sort of spherical symmetry. Okay, so you can think of spherical wave functions as sort of the spherical version of something like a plane wave expansion, right? Or a Bessel function expansion that we did in cylindrical coordinates. Okay, so especially when you want to deal with scattering problems, it becomes useful to kind of discuss spherical wave functions. In fact, in my opinion at least, if you want to really understand antenna theory very deeply, it is important to kind of have good intuition for what spherical wave functions are and spherical expansions are, because a lot of fundamental results in antennas, which we'll discuss a little bit of in this course, for example, super-directivity or small antenna theory, really can be understood much more easily in spherical harmonics or spherical wave functions. A good analogy is something like the first time you learn Fourier transforms, right? Or frequency domain analysis in let's say circuits or systems. It makes things a lot more intuitive. For example, if you want to design a matching network in time domain, it's basically impossible or very difficult, whereas you can design very complicated matching networks in frequency domain. Right? So as we kind of learn frequency domain, we actually become more familiar with frequency domain analysis, right? So similarly, when you want to go deeper and deeper into antenna theory, understanding spherical wave functions and having a good intuition for it actually gives you a nice insight which you cannot get from Cartesian wave functions or general antenna theory. Okay, and also in scattering problems, spherical wave functions become very important. Okay, so having said that, hopefully you're well motivated now to kind of go through the mathematics. The reason I gave you a good few minutes of motivation is because the mathematics actually is fairly technical. So it might look like a little bit of a dry subject, but towards the end, I'll try to give you some kind of a real world example. We'll do super-directive antennas, and you'll see that a lot of beautiful results actually come out of doing spherical wave functions. Okay, so let's get started. So as I said, we did Cartesian and cylindrical coordinates, and the general kind of approach there was to say that if I have some kind of a Hertz vector potential, I can kind of disintegrate that into two parts, e to the I beta z, z hat, right? Or I could also write this as psi of rho comma phi, e to the I beta z, z hat. Right? So the reason you could kind of do this is because in our vector wave equation, let's say the A vector satisfies, which was something like this, plus k square A equal to 0. Right? That could have been decomposed into a transverse part, which is what we did, plus k equal to 0, and a longitudinal part, right? Plus k square A equal to 0. Okay, and since we could do that, we could kind of reduce it into a scalar wave equation, which we know how to solve. But in spherical coordinates, you can't really do that because you don't have this kind of nice decomposition into z and a transverse version, right? You have r, theta, and phi, and there's no easy decomposition because Laplacian in spherical wave functions cannot be decomposed like that. Okay, so in order to kind of come up with a scalar wave equation from the original vector wave equation that the fields and the vector potential satisfy, we need to kind of revisit some of the early lectures that we did where we derived the Lorentz gauge. Okay, in the Lorentz gauge, we saw that we ended up with basically a vector wave equation for A and a vector wave equation for phi, if you remember. That was the magnetic vector potential and the electric scalar potential. And then we said this can be decomposed into, x, y, z, because in Cartesian coordinates, the Laplacian decomposes, or even in cylindrical coordinates, you can do transverse part and this part. But in spherical coordinates, that decomposition is not possible. Okay, so we want to find a different set of potentials that, in fact, do give us some kind of a scalar wave equation. So that's like the motivation to revisit the Lorentz gauge, because under the Lorentz gauge, we don't get something that nice. Okay, so essentially, if we don't use the Lorentz gauge, then the equations that the two potentials satisfy are curl of A minus k square A minus I omega mu epsilon add phi. This is capital phi because we have a little phi for the coordinate mu j. And we also have del square phi minus I omega del dot A equal to minus rho over epsilon. Right? And then we said, okay, we can write this as gradient of divergence minus scalar Laplacian minus the Laplacian. And the gradient of divergence we equate with this, and those terms cancel out, and we get the vector wave equation for A. Right? But we saw that that cannot be decomposed. So we want to go back and see if we can find a better set of potentials that give us the same fields, of course, using a different gauge. Okay? Okay. So to do that, we will simplify it by considering A only has an R component. Okay? And J only has a JR component. So what are we doing here? So we assume that A is along R hat and J is also along R hat. Okay, the reason we make this assumption is that with this we'll see that we end up with a set of field solutions which are the TM to R fields and the TE to R fields. Okay, this is not representing a general field distribution. It only gives you a specific case, and similar to what we did earlier, we can show that that case is enough to act as a basis for any field solution. Okay, it's the same kind of philosophy where we find a specific solution and we show that that's a basis. Okay. So those fields would also be a basis for potentials that don't have only an R component, R hat plus A theta, theta hat plus A phi, phi hat. Okay, the reason that's possible is because the fields will have all components, R, theta, and phi components. Because the fields have all components, and we'll show that the field solutions are orthogonal, and there are infinitely many of them, we do indeed get a basis. Okay, so all the potentials are not kind of specific to only R hat. We do get solutions that have all components. Okay. Okay. So now what we want to do is take this, substitute into this, take this, substitute into this, and then expand out the equation, curl of curl. So once you go through the math, sub and simplify. Okay, that gives you, I'm not going to go through every step, otherwise we'll be stuck here for several hours. But basically that gives dd theta, sine theta, dd theta, plus 1 over r square sine square theta, d square d phi square, plus k square ar is equal to minus I omega mu epsilon d phi, capital phi that is, over dr minus mu jr. Okay, that's one equation. So this is, remember, a vector equation. So we should get three equations. So that's just one of them. The other two equations are 1 over r dd theta dAr over dr minus I omega mu epsilon capital phi is equal to 0. And the last equation is 1 over r sine theta dd phi of ddr ar minus I omega mu epsilon phi equal to 0. Okay. So now we have three equations and we still have the choice of gauge freedom. So what we will do is by looking at these equations, you can see that, I can set this term to 0 by setting this equal to this, right? And by setting this equal to this, both of these equations get automatically satisfied. So this seems like a more natural gauge in spherical coordinates, right? So we'll call this the spherical gauge. Okay. So spherical gauge is then ddr ar is equal to I omega mu epsilon phi. And under this condition, essentially, these two are automatically satisfied. And this guy, this equation up here, reduces to the following. D over dr square plus 1 over r square sine theta, d over d theta, sine theta, d over d theta, plus 1 over r square sine square theta, d square over d phi square, plus k square ar is equal to minus mu jr. Okay, and you can show that this is essentially the same thing as, so this reduces to Laplacian plus k square ar over r is equal to minus mu jr over r. Okay, so you take the expansion of this by using the spherical Laplacian and spherical coordinates, and that will reduce to this equation. Okay, so this is very nice, right? Because this is exactly what we were looking for. We're looking for a wave equation in spherical coordinates, scalar wave equation, and that's what this is. Okay, and similarly, using duality, I have a magnetic current, then you can show that you get a similar wave equation for the magnetic, or this is the electric vector potential under the spherical gauge minus epsilon jmr over r. Okay, so given these two potentials, now you can write the fields. So I'll just write the fields for the electric field. ER is equal to minus 1 over I omega mu epsilon d square over dr square plus k square AR. E theta is minus 1 over I omega mu epsilon r d square over dr d theta times AR. E phi is minus 1 over I omega mu epsilon 1 over r sine theta d square over dr d phi AR, and h theta becomes 1 over mu r sine theta dAr over d phi. H phi becomes minus 1 over mu r dAr over d theta. HR is equal to 0. Okay. And because of this, these fields are known as Tm to R, right? Because the magnetic field along R is 0. Okay. So we saw that AR gives us Tm to R. When you apply duality, you can show that AMR gives TE to R. Okay. Okay. So in general, the field components have all R theta and phi components because it's a combination of Tm to R and TE to R modes. And that in fact forms a basis. Okay. We still have to solve this wave equation to see what the solutions look like. We haven't done that yet. So we want to know what these modes look like. Okay. So we'll define a new potential, psi, is AR over R. Okay, so this means that psi satisfies the scalar wave equation in spherical coordinates r theta phi equal to 0, right? In source-free homogeneous region. Okay, so in a homogeneous source-free region, this is the wave equation we need to solve. Try that again. Okay, so let's actually solve this. So we'll use separation of variables. Now in spherical coordinates, r, theta, and phi, I'll call this r, q theta, f phi. And then substituting and dividing by rqf over r square sine square theta, you end up with implies sine square theta over r, d over dr, r square dr over dr, plus sine theta over q, d over d theta, sine theta, dq over d theta, plus 1 over f, d square f over d phi square, plus k square r square sine square theta equal to 0. Okay, so that's the full expansion of the wave equation, and then we divide by this term. So that gives us this. Okay, so this is nice because we have one term at least that's only a function of phi, and no other term is a function of phi. These terms are functions of r and theta. This is a function of r and theta. Since this is the only function that's a function of phi, right, and everything else is a constant with respect to phi. Since everything else is a constant with respect to phi, this should also be a constant with respect to phi. And we used that argument before a few times, and we've tried to solve wave equations in different coordinates. But that's the argument. Since everything else is constant with respect to phi, this must also be a constant. Okay? So we'll call that constant 1 over f d square f over d phi squared is equal to minus mu squared. And for reasons why we need to put minus mu square there instead of mu will become apparent. But essentially that's what we put in there. Okay, then I substitute this back in here. And so substitute and divide by sine square theta. And you end up with 1 over r ddr r square dr over dr plus a square r square plus 1 over sine theta 1 over q d theta of sine theta dq over d theta minus mu square over sine square theta equal to 0. Now this is also nice because we have this term which is only a function of r, these terms which are only a function of theta. And once again we use the same argument since this is the only thing as a function of r, the rest of it is a constant, so this must also be a constant. Okay, and that must be equal to minus of this one's constant, right? So essentially we'll say that basically this term we'll call equal to a constant nu times nu plus 1. Again, there are reasons we use constants that are specific like this, because they'll end up in a differential equation which we know how to solve. Essentially, and if I set this to be nu times nu plus 1, then this whole thing must be minus nu plus 1, right? So that the whole thing is 0. Okay, so putting these things together, now we end up with essentially 3 different differential equations which are all separable, right? So the final set of equations are d over dr, r square, dr over dr plus ar square, excuse me, minus nu times nu plus 1, r equal to 0. The other equation is 1 over sine theta, d over d theta, sine theta dq over d theta plus nu times nu plus 1 minus mu square over sine square theta q equal to 0. And the last equation was the simplest one, d square f over d phi square plus mu square f equal to 0. Okay, so I'll label these. So we'll call this as 1a, this is 1b, and this is 1c. Okay, so 1c is somewhat easy, right? So 1c implies that f must be some combination of complex exponentials, right? Or you can even use cosine and sine, doesn't matter. But we'll stick to this for now. And we also know that mu is an integer if P is entire domain, which means it includes the entire set of angles from 0 to 2 pi. We saw this because we saw this at the Bessel function case, because e to the I mu phi must also be equal to e to the I mu phi plus 2 pi, which is equal to e to the I mu phi e to the I 2 mu pi. Right? If mu is not an integer, then this is not equal to 1, right? Only when mu is an integer, that's equal to 1, and that's the reason that mu must be an integer. Okay? Okay, so that equation is reasonable. Now equation 1a is actually very similar to the Bessel expression or the Bessel differential equation. Similar to Bessel differential equation, which we saw last time when we did the cylindrical wave functions. And so we know that it has solutions. Of the form r sub n k r is equal to pi over 2kr to the power 1/2 z sub n plus 1/2 kr. Okay, so what is r and z? So z here is my j, n, h1, and h2. So these were the Bessel functions. That's Bessel. So these were the cylindrical Bessel functions, which we discussed in the couple of videos ago. And these are the cylindrical Hankel functions. The first kind and second kind. Bessel is also first kind and second kind. And we said that these basically represent some kind of standing waves. These represent some kind of outgoing waves, outgoing or incoming waves, right? Propagating waves. These are propagating, and these are standing waves. And we saw all of their different properties and so on and so forth. So here, this one now is little j, little n, little h1, and little h2, which are spherical Bessel and Hankel functions. Okay, so they're very similar in behavior to the cylindrical Bessel and Hankel functions. The only difference really is this order, n plus 1 instead of n, and rather n is related to n plus 1. And they also have this 1 over square root of r dependence, right? So they decay a little bit faster than the cylindrical Hankel functions, but very similar properties. Okay, so I won't repeat the properties here, but you can look them up if you like in the book. So which section is this? This section is 8.1. Okay, so properties are very similar, and they are basically your large argument expansions. So we saw that j behaves like cosine, n behaves like sine, h1 behaves like e to the ikr, and h2 behaves like e to the minus ikr. Okay, recursion. We saw recursion relations for Bessel functions. They are very similar in spherical case. And there is the Wronskian relation. Then derivative identities, and so on, right? So we saw all of this when we did cylindrical Bessel functions. I'm not going to repeat them. One more thing we need to address is what is this n, right? So this n actually is new. So we saw that in the Bessel equation, it depends on this new factor here, right? This new times new plus 1. Right? New, actually this should be new, but we'll see that new also must be an integer in a few seconds. Right? And the reason we have to see that, we cannot see that here, is because actually new comes from this equation. Okay, so we saw that mu depends on phi because it comes from this expression. Similarly, nu actually depends on theta because it comes from this expression. So nu is related to theta. So essentially you have to solve for mu from here, put it into this, then you get mu from this, put it into this, and then you can solve this equation. That's somewhat of the progression that we have. Since nu depends on theta, we'll in fact see that for a specific case, which we usually care about is this case of theta, nu also becomes an integer. Yeah, and when it's an integer, then this expression is true. You can find the spherical Bessel and Hankel functions from the cylindrical Bessel and Hankel functions. Okay, so in order to see that nu in fact is an integer, we need to discuss the second differential equation, which is this one. So let's do that next. Oh, before I do that, I just want to quickly mention that section 8.1 goes through all the properties again in the book. You're welcome to read it. But it's very similar in concept to what we did when we did cylindrical Bessel, so I won't repeat it here. I should also mention that sometimes it's more convenient to use slightly different Bessel function. So sometimes we will use what are called Shelkonov Bessel functions. Which are related to the regular Bessel functions by Kr, C, and Kr. Okay. So these are the Shelkonov Bessel functions. Okay, and the reason why we sometimes prefer that is because we know that A is equal to R psi, right? AR is equal to R psi, right? And the Bessel functions and all we saw are solutions when this is in the wave equation. But if you have this, we want to express A in terms of some kind of a Bessel function, the Shelkonov is a better way because it also has this R factor in front of it. So this is related to this, and this is related to this. So basically, when we want to deal in these kind of, in this vector potential A, we'll use the Shelkonov-Bessel functions. I'm just mentioning it. Okay. So, okay, just for the sake of an example, we'll look at what one of the Bessel functions look like. So that x01, that's the Hankel function of the first kind of order 0, is sine kr over kr plus I times minus cosine kr over kr. Okay, and these are nothing but little j0, and this is little n0. Okay, and this turns out to be e to the ikr over kr, ikr. But what is this? This is nothing but our Green's function, right? So essentially, we've just shown you that the 0th order spherical Hankel function of the first kind represents nothing but our Green's function. Of course, the Green's function is 1 over 4 pi here rather than ik, but that's just a constant factor, right? So we know the Green's function represents an outgoing spherical wave. So essentially, a Hankel function of the first kind of order 0 is an outgoing spherical wave. Okay, but we'll see later that even order 1, 2, 3, and so on, they also represent some kind of outgoing spherical waves, and that will establish a very fundamental result in antennas, which we'll see, which is the multipole expansion, which is essentially the basis for super-directive antennas. So we're kind of getting there. So we're building up to that. I just want to take a quick detour and show you some kind of a grounding to reality, because we've been doing a lot of mathematics. Okay, so coming back to the math, we still have to solve equation 1b, rather look at what the solution looks like. And this is in some sense the more complicated one. So 1b. So equation 1b is known as generalized Legendre's equation. And its solutions are the associated Legendre functions. Okay. So we'll see what they are and what their properties are. But basically, they are the associated Legendre functions. So these are again special functions similar to the Bessel function, Hankel function, and so on. There is no simple representation, just because there's no reason for there to be a simple representation. It's a fairly complicated differential equation. But luckily for us, mathematicians have kind of figured out what these functions look like, what their different properties are, and we can use them. Okay, so again, they're of two kinds, P nu mu of cosine theta, and Q nu mu of cosine theta. Okay, so why do we always have these two different independent solutions? Right, we had, in this case, these two functions. In the Bessel equation, we had either the Hankel functions or the Bessel functions, again, they always come in pairs, right? Even for this case, we have like, e to the I and e to the minus I or cosine and sine. The reason is because these are all second order differential equations. That you see there, you have D and D here, D here and D here, and so on. Because they're second order differential equations, they should have two independent solutions. Okay, and for this equation, the two independent solutions are P nu mu and Q nu mu. The reason again we have that nu and mu is because this equation has both of them. Depends on nu, it also depends on mu, right? Okay. So these are called associated Legendre functions of the first kind, and Q is of the second kind. Okay. Mu is the order, which is related to phi as mutual coordinate, and nu is known as the degree, which is related to theta. Okay. All right. So what do these functions actually look like? What are their properties? That's what we'll briefly discuss now. So mu must be an integer. If theta belongs to 0 to pi. Okay, so essentially I'm asserting that if theta is the entire domain, which means contains all angles from 0 to pi, and theta is the polar angle, right? Then mu must be an integer. Why is that? It's not as simple as the case for mu, where we saw that, okay, for periodicity in phi, we need to enforce that mu must be an integer. In this case, the reasoning is a little bit more complicated. Okay, so if mu is not an integer, and theta contains both 0 and pi, then P becomes multiple valued. But loosely speaking, P becomes multiple valued. Okay. And if you know what a branch cut is, then you can actually show that there is a branch cut -1 to 1. Okay. So if you don't know what a branch cut is, don't worry about it. But basically, when you include all angles of theta and mu is not an integer, then P can have two solutions, similar to like a square root function, right? A square root function has two solutions. Square root of x is plus or minus square root of x, basically, right? Log also has multiple values, right? Like for example, we know e to the ix plus I2 pi is equal to the same thing. If I take log on both sides, and log a has many solutions. Like log a is ix plus I2 and pi. It has many different output values. Those are all multiple valued functions. So when you have complex arguments to multiple valued functions, you need to treat them carefully. You need to know what a branch cut is or branch point is, but we won't go into all of those technical details here. I'll just mention it that p becomes multiple valued, and that's the reason that nu must remain an integer, because in physics, we can't have real multiple valued functions, right? So for example, if you want looking for solutions to the Maxwell's equations, we know they are unique. So you can't have two different solutions that are both valid. And that's the reason you can't have two different values of P, because then you would have two different potentials that give you the same, that are both equally valid, which means you have two different solutions. Right? That's not possible. Okay. Also, Q cannot exist. Okay, because Q of plus or minus 1 goes to infinity. Okay, so Q basically becomes singular at plus or minus 1. Because Q becomes singular at plus or minus 1, cosine theta equal to plus or minus 1 means theta equal to 0 or pi. So if 0 and pi are included in the domain, then Q also cannot be included. Okay, so you only have one admissible solution. So essentially, if you write, the full solution as a linear combination, so let's say A mu nu, P mu mu plus B mu, sorry, let's just say A mu mu plus B Q nu mu. If I write a linear combination of both, and theta includes 0 or pi, then this coefficient must go to 0, because otherwise this will blow up, right? And that's the reason that this cannot be an admissible solution. Okay, so whenever theta includes the entire domain, so theta belongs to 0 to 0 to pi, implies P n m of cosine theta is the only admissible solution. There are really cases where Q also comes into play. For example, if I have a disc cone antenna, something like that, and I want to find what is the radiation here, then theta equal to 0 and pi are not included. So then you have to still include Q. But the order and degree will still be equal to integers, right? Because the branch cut actually exists pretty much in the entire domain. So you would still have to have integer values for the order and degree. Okay, another constraint is that m is always less than or equal to n, because P and m of x equal to 0 for n greater than n. Okay, so we don't exactly know what this P function looks like yet, because we haven't looked at expressions for it. But basically, we can show from their different expressions. And there's no simple representation. I'll show you at the very end one representation. But basically, since this goes to 0, there's no need to consider values of m that are greater than n. Okay? Okay, so what does these functions actually look like? So let's see that. So we'll treat just a couple of cases. So okay. So here I'm drawing Pn0 of x. Okay, these functions look something like this. Okay, so that's P1, and then P2, just like that. Actually, this is P2. So P1 is just a straight line, it's just a constant. Not constant, just linear. That's P2. Then maybe I'll draw P3 in a different color. Sorry, should start from here. It's P3. And then P4. Something like that. Should use a different color. This is P4 and so on. Okay, so they look like some kind of functions, polynomials really. In fact, these are called, when the degree is 0, they are called the Legendre polynomials. Okay, so they do have simple polynomial expansions when the degree is 0. And then for higher degrees, for 1, 2, 3, and so on, you can look up tables and see what the functions look like, but they look very similar to this. So something like this, or like this, or like that, or like that, and so on, right? So these are all different in X for different degrees and orders, okay? The nice thing actually about Legendre polynomials is that they independently form a basis for functions that lie between -1 to 1, with domain between -1 to 1. So they're actually quite popular, famous, but this is only for degree 0. The associated Legendre polynomials become the Legendre polynomials. Okay, for all of the degrees, they are known as the associated Legendre functions or associated Legendre polynomials. Okay, so again, these functions also have many properties. I won't go through all of them here. Whenever we need to use a specific property, I'll bring it up, but you can kind of look up the properties in the textbook or in any other reference book. But I'm going to stop the discussion on Legendre polynomials here. We will essentially develop the very basic properties that we do need. Okay, and let's move on to the physics now. Okay, so in general, I have a expansion for my psi function, which is a function of r, theta, and phi, summation over n, summation over m, which are my mu and nu index, an, jnkr plus bn n sub nkr times bnm cosine theta e to the im phi. Okay. So let's just recap. This is the spherical Bessel function of the first kind, spherical Bessel function of the second kind. This is the associated Legendre function or Legendre polynomial of the first kind. This is just an exponential function, right? So the Bessel functions represent standing waves in R. These guys represent some kind of polynomial function in theta. This is just our cosine and sine and phi. Okay, so the combination of all of these is called the spherical wave expansion. So this is in fact the spherical wave expansion. Okay, so all of these functions basically form a basis. This is exactly the basis actually. So this is the basis expansion of some kind of a function in r, theta, and phi, which satisfies the wave equation, can be expanded in terms of these functions. If the origin is included in the domain, then this must be 0, right? Because we know that this goes to infinity when r goes to 0. So essentially, you'll only be left with this part if you're including the origin in the domain of the problem. Okay. So one more special case is this. So these are called spherical harmonics. Spherical harmonics. Okay, they're called spherical harmonics because these functions actually, just this part, the theta and phi dependence, the associated Legendre polynomial, and the e to the im phi, these form a basis for any function that lies on a sphere. Okay, so sometimes they are written as y and m, theta comma phi. Okay, so any function that lies on the surface of a sphere can be expanded in terms of just this part. For example, if you want to map the gravity on the surface of the Earth, right? That's a scalar function in theta and phi, and that can be expanded in these spherical harmonics, okay, because r is essentially constant, right? So here we've shown that this is for a function that satisfies the wave equation, but this forms basically a basis for many functions, not just functions that lie, that solve wave equation, for many functions that are somewhat continuous or smooth on the surface of a sphere. Yeah, it's kind of interesting to know, and that's why they're called spherical harmonics. They show up in quantum mechanics as well. Okay, so what kind of functions are, so for example, the directivity pattern of an antenna is only a function of theta and phi, right? So this should be able to expand this in terms of a n m e n m e to the I m phi. Right? That's a function on the surface of a sphere, only a function of theta and phi. So you should be able to expand it in terms of the spherical harmonics, right? And we can take a single example. So I'm taking the delta function in theta and phi. Of course, this is not a realistic directivity pattern. It's the ideal directivity pattern of a antenna that has an infinitely thin beam. Right? So what do these delta functions mean? That means that this beam only exists in one direction, right? It's basically an extreme antenna that has an infinite directivity in one direction. Okay? So this is a mathematical result. So n equal to 0 to infinity, m equal to 0 to n. We only need to consider up to n because all the other values of m are 0. So you can show actually that this mathematical identity is true. Over 4 pi n minus m factorial over n plus m factorial pnm of 1, where alpha m is equal to 1 when m equal to 0, equal to 2, and m is greater than 0. So that's your coefficient. That's your basis. Here there's no e to the im phi. M is basically 0. You can think of it as, no, m is not 0. This function is not required in this expansion because there's no variation in phi, I guess. Right? So you're essentially left with just this. Okay. So this is nice. So you can actually look at this example. This is from one of the examples in the book where they show you how you can calculate this. And the reason this is somewhat useful is because you can kind of approximate a highly directive beam. So this is for the extreme case of infinite directivity. But if I truncate this expansion, right, if I don't use infinite number of terms, I use, let's say, 10 terms, then instead of a delta function beam, you'll have a beam with very high directivity, right? So you can look at this in the book. So this is example 8.1 in the book. And the reason I'm presenting it here because we'll talk about this at the end of today's lecture. Okay? All right. This comes out to be a very fundamental result. Okay. So far we've looked at spherical wave expansion. So we said, okay, we can change the gauge, the Lorentz gauge to some other gauge, the spherical gauge, and end up with this wave equation in spherical coordinates, which leads to TE and TM modes. And we saw that those modes basically look like a combination of Bessel functions, Legendre polynomials, and exponentials. And we saw that that forms a basis. So we haven't really proven that it's the basis. We haven't proven the orthogonality. It's a bit long, so I'll leave it for the book. But since we've shown it in the past, I don't want to do it again. You can look at orthogonality in section 8.1.4. But basically, these functions are orthogonal. Okay, so they form a basis. Okay, so the next thing we want to do is essentially derive a very fundamental result in antennas, which in some sense actually contradicts something that we did earlier. So this is called the multipole representation of spherical wave functions. So what's the big idea here, right? So earlier we showed that Hn0 or H01 was nothing but the Green's function, right? So essentially we know that the Green's function by definition is the radiation coming from a single monopole or a single small current distribution or point current oriented in some direction, right? And here we would like to show that a single current obviously gives a H0 function, which is one of the basis functions. But every single basis function in this spherical wave expansion, every single basis function corresponds to one distribution or orientation of point currents. Yeah, that's the big idea here. And that actually leads to a very fundamental result. Okay, so let's see. So if I'll just make copies. So I have some kind of coordinate system that X, Y, Z. Right, so I have one case. So let me actually make copies of this. Say I have something here. Another case. Do one more. Okay. Okay. So we have many cases. So we'll take the simplest case, which is just a single current, point current along Z. So we'll call this the monopole case. And although it's really a dipole current, small current, but we'll treat it as a monopole here. That's the terminology we'll use. Or you can call it the dipole zero, or multipole zero, multipole number zero. Okay, anyways, so that's monopole. And then we can also do dipole. We have one current going up, one current going down, oriented in Z, or we can have them oriented along the y-axis, or along the x-axis. These are all dipoles. So this is dipole 1, dipole 2. This is dipole 3, and so on. And these are the three cases. And then we can also do quadrupoles. So quadrupole would be many different types. One type is what I'll draw here, going up, going down. And let's just assume that this is in the YZ plane. This is the YZ plane. And of course, you can have it in XY plane, XZ plane, and so on. And then they can all have different orientations. Okay, so what we want to show is that each of these cases, monopole, dipoles of different kinds, and quadrupoles, and all the multipoles. So these are all called multipoles. So this is a quadrupole, and so on, right? So these are all multipoles. Each multipole gives radiation, which corresponds exactly to one of the basis functions in this expansion. That's what we want to prove now. Okay, so we know that this will give us the Green's function. Right? That's trivial, which is H01. And that's the definition of the Green's function. And then we want to show that this gives another spherical harmonic. This gives another spherical harmonic. This gives one, and this gives one, and so on and so forth. Okay. So what's the big idea here? How do you actually do this? Right, before we do the math, the idea is you take this monopole and you take its derivative. And we'll see that the derivative of this monopole is actually this dipole. Okay. Similarly, you can take a derivative along x and y, and you get these two cases. Then you take derivative of this along x and z, and you get this, right? Or rather, this one gives the derivative here. Right? Because when I take derivative of this, it splits into one going up and one going down. Similarly, this will split into one going down and one going up, and we'll see why that is. But essentially, that's what's going to happen. Okay, you can even see intuitively why that is. So if I have a point current, right? So let's say I have a point current in Z. If I actually plot the current, That's nothing but a delta function, right? So I'll take the close approximation to a delta function, which you can think of as something like that. Right? In the limit, this becomes a delta. As this becomes smaller and smaller, this goes higher and higher to preserve the area, and that's how you derive a delta function, right? So the derivative of this is this function, right? So this is sometimes called the doublet function. And this is the Dirac delta. And that's essentially, if you take this doublet function to the limit, then this becomes infinitesimally small, this becomes small. So essentially, there are two singularities now at the same point. Right? Dirac delta only has one singularity, but doublet becomes two. But essentially, that is nothing but what we have here, right? One positive current, one negative current. And both of these actually should be kind of at the origin. Here we're taking current that's something like this, right? And if you take another derivative, and so on, then you end up with these cases, right? So what we are trying to show here is that any function, so if you put all of this together, right, let's go back one step. I said that any function can be expanded in this spherical harmonic basis. And then I show you that every basis function is nothing but some combination of these multipoles, right? And we said that every multipole can be derived as some kind of a derivative of the original monopole. So what are we saying? We're saying we have a function and we can represent it as some function and its derivatives, right? And so on. What's that? That's nothing but a Taylor series. Like, what is a Taylor series? A Taylor series says that I can expand a function at any location by just the function at some point plus its derivatives at that same point. And there's some coefficients, of course, second derivative and so on. That's a very, it's really an amazing result, right? I have some function. I want to know what its value is everywhere. If I want to know what its value is at some point here, and I know its function, I know its value here and all of its derivatives at a single point, then I can find the function's value at any different point. That's the meaning of a Taylor series, right? So here it's the same thing. We're saying that we have some complex representation of the radiation field, and I can essentially give you that representation by knowing what all of these multipole expansions are. Right? So multipole expansion is really some kind of a spherical version, a spherical 3D version of a Taylor series. That's at least how I think of it. But we'll see actually that it gives very fundamental results in antennas. I'm going to erase this part, and then let's actually prove this. Proof. So you want to prove that every single monopole or every multipole corresponds to one unique basis function in the spherical wave expansion. Okay. So we know that for a single monopole of current, the vector potential is given by mu I dl over 4 pi e to the ikr over r. And we did this many, many lectures ago when we discussed Hertzian current element. Right? But this was the Lorentz gauge. So this is under Lorentz gauge. Okay. But now we are dealing with spherical wave expansions in the spherical gauge. So how do we find what it is in spherical gauge? We know fields are unique. So we can first find the field and then take the field to the spherical gauge. That's the trick. So I can kind of rewrite this as I mu ki dl over 4 pi times h01 kr, because h01 kr is e to the ikr over ikr. So I pull the ik out here. Then I have the 4 pi here, the mu and idl is still there. Right? And I can put this as P naught of cosine theta. because P naught of cosine theta actually is nothing but a constant 1. Okay, so this becomes 1. This becomes e to the ikr over ikr, and then everything's all in good. Right? The reason I write it like this is we'll see later, because this corresponds to the 0th monopole, right? At 0, P0. Okay, but we want to take this to our spherical basis, a spherical gauge. So let's do that. So we know that the H field for this vector potential is k square IDL over 4 pi minus I plus 1 over kr times e to the ikr over r sine theta p hat. Okay. And we know earlier we saw, or we didn't show this maybe, but basically H phi, the phi component, you can get from the spherical gauge using this expression over d theta. So this is the spherical gauge now. That's the vector potential under the spherical gauge. So it's important to keep track of them because gauge gives you a different potential, right? Now comparing these two, you can actually show it easily that the spherical gauge AR must be mu k square IDL over 4 pi times minus I plus 1 over kr e to the ikr cosine theta. Okay, you can very easily show this. You take the derivative with respect to theta, and then cosine theta becomes sine theta, and everything else remains the same. And of course, you have this term and this term as well, but it's very easy to go from here to here. Okay, so now note that, so this is one of the properties of the Shelkenov-Bessel function of type 1, order 1, is nothing but minus 1 plus I over kr e to the ikr. And you can derive this from the properties, Bessel functions. And P10 of cosine theta is actually nothing but cosine theta. That's also one of the expressions. That's just the Legendre polynomial. And so I can rewrite that potential as I mu k square I dl over 4 pi h1 hat 1 kr P10 of cosine theta. Okay? And this is nothing but one of the unique spherical wave expansions. Right now we're writing it in terms of Shelkenov-Bessel functions because we have A instead of psi. If we use psi, then this would be H over R, right? H1 over R. But that doesn't matter. This is a unique basis function or spherical wave function because both these indices are the same. Like you have Hn, T, and M. Right? So n equal to 1 and m equal to 0. That's a unique mode. Right? So this coefficient is nothing but A10 in our spherical wave expansion. Okay? So in spherical gauge, this is nothing but the A10 mode. Right? Or the A10, yeah, mode, or you can call it the A10 multipole. But if you go back here, we just showed that it's a unique multipole in the spherical gauge, but it's really okay to also look at it in terms of the Lorentz gauge. But even in Lorentz gauge, you have this same basis. And you don't have to really take it to spherical gauge. So in Lorentz gauge, actually, it is A00. At the end, you get the same fields. Right? So doesn't matter. So we'll just deal with the Lorentz gauge for now. A00 multipole. And each gauge in the Lorentz also becomes a single function, sorry, a single potential which represents a single harmonic in Lorentz gauge, becomes a single harmonic in the spherical gauge as well, which we haven't proved, but just for the sake of simplicity, we'll just deal with the Lorentz gauge. Okay. Okay, so that's the simplest case. So this was of monopole basically. Right. Now we want to see for the dipoles. These two dipoles. We want to show even for dipoles, you have a unique spherical wave function coming out. So AZ2 would then be AZ1. So AZ2 represents a dipole. So we shift this monopole by minus delta over 2 and delta over 2, xy plus delta over. So this is the first dipole case, right, where we're moving it up and down in Z. So we have a plus and a minus to represent the plus and minus. And this is nothing but delta times d az prime over dz. That's the definition of, not prime, sorry, 1. So this is 1. This is also 1, this is also 1. And 1 represents the monopole case. And this is equal to, you can take the derivative, would be minus I mu ki dl delta over 4 pi d over dz h01 of kr. So I've taken AZ1 from directly from here. So this is the Lorentz gauge version. Okay. Okay. So we know from derivative, can show from derivative properties. From derivative properties, this is equal to I mu AIDL delta over 4 pi H11 AR cosine theta. Okay, and the cosine theta actually comes from dr over dz. Right? When you apply chain rule to this, you have to take d over dz, apply it to this r. That gives you the cosine theta. And derivative of the Hankel function order 0 becomes order 1. Okay, but this is nothing but, oops, it's too big. That's nothing but P1 cosine theta, right? That's the genre polynomial of order 1. Okay. So what does this mean? This means again, this is nothing but one of the spherical basis functions, right? So again, we get a nice basis function of a certain kind, right? Which one is it? Now this is n equal to 1 and m equal to 0. Okay, similarly, you can take the case for a2 x. See, so now we are shifting in x, so this was shifted in z. So if you shift it in x, you can show that this gives you I mu ki dl delta over 4 pi h11 ar p11 cosine theta times cosine theta in case of the x case and sine theta in case of the y case. So I should say x comma y. And that's, sorry, this should be phi, not theta. But again, it's because of the dr over d x or dr over dy, right? On the chain rule. So both of them correspond to n equal to 1 and m equal to 1. Either the cosine case or the sine case. Those are degenerate, right? So this comes from the fact that you take minus delta daz1 over dx or y. Okay, x or y. Okay, so we can kind of do the same thing for the quadrupole. So quadrupole, I'll just write the final expression. 4yz represents the yz plane, delta 1, delta 2, d square az1 r over dy dz gives you minus I mu k square I dl delta 1 delta 2 over 12 pi times h21 ar p21 cosine theta sine phi. So this corresponds to n equal to 2, m equal to 1. Okay, so like that, you can go on building the higher order spherical wave expansions, and you'll get different coefficients for each case. But the idea here is to just show you that for order n, you will need a 2n element multipole. Okay, and m is determined by the orientation of those multipoles. Okay, and of course, m is always less than or equal to n. Okay, so I said earlier that this gives you a very fundamental result in antennas. What is this fundamental result, right? And how does it contradict what we've done earlier in antennas? The fundamental result it gives here is what is called a super-directive antenna. Okay, so this is, it's kind of become a little bit popular in the last few years, but it's kind of an old concept, really. Okay, so since spherical wave expansions have existed, people have known about it. What's the idea here, right? So we said that, okay, I can take a highly directive radiation pattern, highly directive direct radiation pattern, let's say, right? Like delta theta, delta phi over sine theta that we discussed, something like this. Okay, then I can decompose into my spherical wave expansion, right? So I can do that. It's the double summation we saw earlier in the example. And then I can realize the spherical wave expansion with multipoles, right? So basically, I have my coordinate system like this. I have some kind of multipole combination. Maybe there's one here, one there, one there, and so on and so forth. Right? I can pack all of these tight multipoles in a very small region. And this is really an infinitesimally small region. So this whole thing is infinitesimal, right? Infinitesimally small. Let me actually do that again. So this is infinitesimally small because the multipoles are really very close to the origin. Right, so I can create this kind of multipole expansion, put all of these multipoles in an infinitesimally small ball, and recreate exactly the same highly directive radiation pattern, right? But that's a contradiction in some sense, because earlier we said, when we discussed that the far field radiation pattern is a Fourier transform of the current distribution, we said that you do need a very large aperture in order to get a very small or beam or narrow beam. Right, so this is in contradiction Is it in a contradiction with lambda over d? Right? We said that the wavelength is kind of, or not a wavelength, the beam width is approximately lambda over d. Right? So if you want a narrow beam or high gain, you need a very large diameter or very large aperture, right? It also is in contradiction with lambda square over 4 pi times g. That was the aperture. So if you have a very large aperture, you will have very large gain. And but that seems to contradict this because in this case you have a very small aperture but very high gain. Right? So is it really in contradiction? The answer to that is no, it's not. Okay. And we won't go into the detail, but the basic idea is that the current distribution here is highly singular. Right? So as we said earlier, you have like Dirac delta, its derivatives and its derivatives and its derivatives and so on. All of those derivatives are highly singular functions, right? So your current distribution looks something like a very discontinuous function, right, in a very small space. Now, what is the Fourier transform of this? A highly singular function. You can still take Fourier transforms, right, because it still has finite energy. So we know that for a delta function, the Fourier transform is a constant. If I take the derivative on the left-hand side, in Fourier transform space, it's e to the ikr, or something like that, right? And then if I take another derivative, it becomes e to the I2kr, of course, with some kind of coefficients here, a, b, c, and so on, right? So you're essentially adding up highly oscillatory functions on the right-hand side. So in K space, you have something that's oscillating like crazy, right? So when you add up all these oscillatory functions, you can get a very singular or very narrow beam in K space. A K space narrow function that's narrow in K space corresponds to a narrow beam, right, from the plane wave expansion or angular spectrum. So essentially, you're adding up highly oscillatory functions to get a narrow beam, and they come from the fact that you have a highly singular function in the current distribution. Okay, so in theory, this is all well and good. In practice, actually, you cannot get that high gain. Okay, so I should say note. In practice, the directivity improvement is somewhat modest. Okay, why? Because of mutual coupling. First thing, here all of you kind of assumed ideal current distributions that don't couple to each other, right? Linearity in some sense we've assumed, but that's not really true, right? When you have small currents that are next to each other, they will couple. Another limitation is high currents. You need very large currents, right, to actually have some power in this system. If you go back here, you can see that I have these deltas in the numerator, right? So if you make the monopole very small or the multipole very small, then I have to have very large currents. And it gets worse and worse for higher values because you get more and more deltas here. So taking higher order derivatives you need more and more current. Right? And more current means more and more coupling, power dissipation, and so on. Right? The other big issue is efficiency. Efficiency and bandwidth. So we haven't really derived this result, but this is a very fundamental result in antennas, which relates the bandwidth and efficiency of an antenna, especially for small antennas. And of course, this is a small antenna, right? Electrically small antenna. Because it's an electrically small antenna, it has to satisfy a bandwidth efficiency constraint, which is called the Chu-Harrington limit, which we will maybe derive in the future. But basically, these antennas are not efficient, or they have very, very narrow bandwidths. Okay, so because of these practical considerations, the gain enhancement is usually not very large, but indeed you can, get some modest directivity improvement for a given size antenna. Right? So super-directive basically means that the directivity is higher than an equivalent antenna that has a uniform aperture current distribution, which is very similar to lambda over d. Approximately gives you lambda over d, and the aperture is large at least. Okay, so if I take a uniform aperture current distribution, and then I calculate the far field gain or the far field directivity, compare it with my kind of this funky looking antenna, which has all of these singular currents, and then I see that what I have gives me high directivity, then you can call it a super directive antenna. So that's the idea there. So we basically saw that this fundamental result, super directive antennas, comes from the mathematical properties of all of these special functions, right? The way they take derivatives, which is the Hankel and the Hankel function and the Legendre functions, right? And in fact, even the bandwidth efficiency limit can be derived from properties of these functions. A beautiful result that was derived many years ago in a very beautiful paper, actually. But basically, the functions that we have in spherical wave expansions have really nice properties, derivative properties, recursion relations, Wronskian relations, and so on. And we actually exploit all of these properties to extract a lot of amazing physics, right, in antenna design and antenna theory. So we've done a little bit of that today in super directive antennas, but essentially that's why hopefully now you're kind of motivated. You see that spherical wave expansions and thinking of functions or radiation problems, scattering problems in spherical basis gives you a lot of nice insight, right? Okay, so long video today, but hopefully it was enjoyable. If you have any comments, you can leave them in the comment section below. If not, I'll see you in the next one where we discuss scattering from spheres. All right, thank you.